The Great Pyramid of Giza stands as a monument not just to a pharaoh, but to a seemingly impossible feat of engineering. For over 4,500 years, its shadow has stretched across the desert, concealing a fundamental paradox. 2.3 million stone blocks, averaging 2.5 tons each, were stacked with astonishing precision to a height of nearly 500 feet. To achieve this in just over 2 decades, one block had to be set every 5 minutes of every daylight hour. The logistical challenge is immense, but the core engineering mystery is one of pure physics. How was this colossal mass lifted? The theories of lost high technology are tempting, but the truth is far more ingenious. In this video, we will not speculate, we will analyze. This is the definitive engineering breakdown of how it was truly achieved. The long-accepted hypothesis posits a massive external ramp, a singular, straight causeway growing alongside the pyramid. Yet, as our initial schematics will demonstrate, this solution presents its own set of impossibilities. To maintain a manageable gradient for hauling multi-ton blocks, such a ramp would need to extend over a mile from the pyramid's base. The sheer volume of material required for its construction would have equaled or even surpassed that of the pyramid itself, an absurdly inefficient project that would have left behind a mountain of evidence. Yet, no such evidence exists. This is the first critical failure in the traditional model. It is not a viable engineering solution. To fully appreciate the flaws in the external ramp theory, we must deconstruct it with forensic precision. Let's begin with the straight ramp model, the most commonly depicted solution. As our 3D model now illustrates, for a team of workers to haul a 2.5-ton block up a slope, the gradient cannot exceed 8%. Any steeper, and the coefficient of friction combined with the sheer force of gravity makes the task impossible for human power. The physics dictates a ramp length of over 1.6 kilometers, or 1 full mile, to reach the pyramid's apex. The logistical implications are staggering. This ramp would require approximately 400,000 cubic meters of material, a volume representing nearly 30% of the pyramid itself. It would be a second, monumental construction project, built and then laboriously dismantled, leaving behind a quarry's worth of debris, for which there is zero archaeological trace. Recognizing this, proponents have suggested alternative models, such as a zigzag ramp switching back and forth on one face of the pyramid. While this solves the length issue, it introduces a new and far more dangerous engineering problem: the corners. Our simulation demonstrates the forces at play. On each turning platform, a multi-ton block must be pivoted 180 degrees on a narrow ledge, hundreds of feet in the air. The space is insufficient for a wide turning arc, meaning the block must be levered around a tight pivot point. This action concentrates immense pressure on the corner of the ramp, a point of critical structural weakness. The risk of catastrophic failure on these unsecured temporary platforms would have been constant. Furthermore, the efficiency of the entire operation would grind to a halt at these bottlenecks. The constant fluid movement of blocks required to meet the construction timeline becomes an impossibility. The final major external theory is the spiral ramp, which corkscrews around the pyramid's exterior. On the surface, this appears to be the most elegant solution. It grows with the structure and keeps the gradient manageable. However, it suffers from a fatal architectural flaw. The Great Pyramid is not merely a pile of stones. It is one of the most precisely aligned structures on the planet, oriented to true north with an accuracy of within 1/15 of a degree. This feat of surveying required clear, unobstructed lines of sight to the pyramid's 4 corners and faces throughout the construction process. An external ramp, as our model shows, would have completely shrouded these crucial reference points. The builders would have been working blind, unable to make the precise measurements that define the pyramid's geometric perfection. The flawless final structure serves as definitive evidence that its exterior faces could not have been encumbered by a massive ramp. Beyond the geometric and logistical failures, all these external models share a fundamental material science problem. They would have been constructed from mud, brick, and desert rubble, or TAFLA. Our material analysis shows that such a structure would be dangerously unstable under the required load. Imagine the compressive force of a 2.5-ton block, combined with the weight of dozens of workers concentrated on a small wooden sled. This load is applied repeatedly for 20 years, grinding away at the ramp's surface. Rain, though infrequent, would turn a taffla ramp into a treacherous mudslide. The constant maintenance required to prevent collapse would have consumed a colossal amount of manpower, crippling the primary construction effort. The conclusion from our forensic analysis is inescapable. No external ramp model, straight, zigzag, or spiral, is compatible with the laws of physics, the principles of logistics, or the archaeological evidence on the ground. The solution must lie elsewhere. The failure of every external ramp model forces our investigation inward. If the solution is not on the outside of the Great Pyramid, then architectural logic dictates it must be on the inside. For decades, this was mere speculation, but recent evidence has transformed it into a verifiable engineering reality. The first clue is a subtle anomaly, long dismissed by many, located on the pyramid's northeast corner, about 85 meters up. Known as the notch, it's a small, irregular gap in the structure that defies explanation in any conventional construction model. However, our analysis reveals it to be something profound, a critical piece of the puzzle. This notch is precisely where a spiraling internal corridor, if it existed, would need an open corner to pivot a long block. It is a construction scar, left unsealed, giving us a window into the pyramid's hidden anatomy. This physical clue is now supported by cutting-edge scientific data. In 2017, the Scan Pyramids project used a technique called muon tomography, a particle physics method that can detect density variations deep within solid structures to probe the pyramid's core. The results were revolutionary. The scans revealed a massive, previously unknown void, at least 30 meters long, located directly above the Grand Gallery. More importantly, they detected other linear voids forming a pattern consistent with an ascending corridor. When we map these density anomalies onto an architectural schematic, they align perfectly with the trajectory of a ramp spiraling upwards at a consistent, gentle gradient of approximately 7 degrees. The data provides a non-invasive, high-confidence confirmation. There is a hidden internal structure winding its way up through the pyramid. Now, with our 3D animation, we can reconstruct this ingenious system and reveal, for the first time, how it truly worked. The process begins at the base. For the first 30 to 40 meters, the builders utilized a short, wide, external ramp. This allowed for the rapid placement of the largest foundation blocks, establishing a massive, stable footprint. This initial ramp is consistent with the limited archaeological evidence of construction causeways found near the Giza Plateau. But once this base was complete, the strategy shifted. The external ramp was abandoned, and construction moved inside. As our model deconstructs the outer layers, you can see the internal ramp taking shape. It is a rectangular corridor, approximately 2 meters wide and 3 meters high, running parallel to the outer faces of the pyramid, about 10 to 15 meters in from the edge. This placement is a stroke of structural genius. It uses the immense mass of the pyramid's core as its load-bearing foundation, eliminating any stability issues. The blocks were hauled up this internal corridor on wooden sledges. Upon reaching each corner, the corridor opens into a small, unroofed platform, the very feature that creates the external notch. This open-air corner provides the necessary space for a simple but effective lever and pivot system to rotate the sledges 90 degrees and send them up the next leg of the ramp. This solves the fatal cornering problem of the external zigzag ramp with elegant simplicity. This integrated system also explains the pyramid's incredible surveying precision. With the ramp hidden inside, the 4 exterior faces remained clear and accessible. As our simulation rebuilds the pyramid layer by layer, watch how the surveyors on the outside can continuously check their crucial sightlines to the corners and the apex, ensuring the geometric perfection of the outer casing stones. They weren't building blind, they were working on a stepped core structure, with the internal ramp feeding blocks from within. The smooth white Tura limestone casing was the final element to be installed at each level, sealing the ramp behind it as the pyramid grew. This model fundamentally recontextualizes the pyramid's known internal features. The Grand Gallery, with its soaring corbelled ceiling and 26-degree slope, has long been an architectural marvel and a symbolic mystery. Our engineering analysis shows it was also a masterpiece of functional design. It acts as a specialized, high-capacity section of the internal ramp system, a central causeway allowing for the transport of the colossal granite beams, some weighing up to 80 tons, used to construct the roof of the king's chamber. The grooves and notches along its walls are not merely decorative. They are anchor points for a complex rope and pulley or counterweight system needed to manage these super heavy loads. The Great Pyramid is not a structure with a single ramp. It is an interconnected system of ramps. A short external ramp for the base, a main internal spiral for the bulk of the construction, and the Grand Gallery as a specialized heavy lifting artery at its heart. This is the solution that fits all the evidence, the physical notch, the microgravity data, the architectural precision, and the unique design of the internal chambers. It replaces speculative fantasy with elegant, efficient, and achievable engineering. The internal ramp is more than just a clever solution to a lifting problem. It represents a paradigm shift in our understanding of ancient project management. It is a fully integrated system where the means of construction is woven into the very fabric of the final structure. This approach is a hallmark of sophisticated, systems-level engineering thinking. The builders of the Great Pyramid were not just piling stones. They were executing a multi-stage logistical master plan that solved the challenges of stability, material transport, and surveying precision simultaneously. By moving the primary causeway inside, they created an all-weather, structurally sound highway that was shielded from the elements and grew organically with the monument. This principle of integrated construction pathways is remarkably modern. As our comparison schematic now illustrates, the same core concept is used in the construction of today's super-tall skyscrapers. Modern engineers use a climbing formwork system where the central elevator core is built first, rising ahead of the outer floors. This core then serves as the structural backbone and the primary conduit for lifting materials via integrated cranes. The Egyptian builders, in essence, devised a 25th century BCE version of this. The pyramid's massive core was their backbone, and the internal ramp was their material conduit. It demonstrates a profound understanding of efficiency and resource management. Build the transport system once, use it for the duration, and seal it within the finished product, leaving almost no trace behind. This re-evaluation transforms the Great Pyramid from a brute force mystery into a monument of intellectual brilliance. The true marvel is not some lost exotic technology, but the human capacity for observation, planning, and systematic problem-solving on an epic scale. They recognized the inherent flaws in external structures and pivoted to a solution that was more complex to design, yet vastly more efficient and elegant to execute. The answer to the paradox was not found by looking for a bigger ramp, but by fundamentally rethinking the relationship between the structure and the process of its own creation. The scientific method, from muon tomography to forensic architectural analysis, has allowed us to peel back the layers of stone and time. In doing so, we have replaced a persistent myth with a far more impressive reality. The story of engineers who mastered physics and logistics to build an eternal monument from the inside out. If this definitive breakdown has reshaped your understanding of this ancient wonder, support our work by subscribing and activating notifications. Join our next investigation as we deconstruct another engineering impossibility. For exclusive access to our research notes and 3D models, consider supporting us through the links below.